Here are homework corrections for page 241, 6 through 8. Question number 6 says, balance this equation. So first it asks us to balance this equation. This is a combustion reaction. So we have 2 carbons, so we need a coefficient of 2 in front of carbon dioxide. We have a total of 5 plus 1 more is 6 hydrogens, so we need a coefficient of 3 in front of water. So now we have 4 plus 3 makes 7 oxygens. I have 2 here and 1, so I can use a coefficient of 3 in front of oxygen to get 6 plus 1 makes 7. Letter A asks us to interpret this equation in terms of numbers of molecules and moles. Sorry about that. So in terms of molecules and moles, so again, molecules really is kind of asking about representative particles. Because all of these substances are molecular compounds, they're all going to be molecules. Remember, to interpret in terms of representative particles, our coefficients tell us the relative numbers. So for representative particles, we're going to have 1 molecule of this alcohol. We're going to have 3 molecules of oxygen because the coefficient is 3. 2 molecules of CO2 because the coefficient is 2. And 3 molecules of H2O because the coefficient is 3. Interpreting this in terms of moles, again, for interpreting in terms of moles, the coefficients give us the numbers. So we have 1 mole of this alcohol, 3 moles of O2 because the coefficient is 3, 2 moles of CO2 because the coefficient is 2, and 3 moles of H2O because the coefficient is 3. Right, so we already balanced this, right, once, so we'll just put our coefficients in here. Okay. So letter B asks us to show that the balanced equation obeys the law of conservation of mass. So again, this is math required. All right. So to do this, again, we're going to start with moles, and we're going to start with the number of moles from our balanced equation. So we're going to have 1 mole of, again, our alcohol. We're going to use molar mass. 1 mole of our alcohol is going to be 46.0684 grams of our alcohol, which gives us right, that's pretty easy math there. Then we have oxygen, and we're going to start with 3 moles of oxygen. I'm going to use oxygen's molar mass. Again, I get this number I'm writing right now from adding up 2 oxygens on the periodic table. I get 95.994 grams of oxygen. Okay. For carbon dioxide, I'm going to start with 2 moles because that's my coefficient. I'm going to use again the molar mass of carbon dioxide, which is 44. Okay. And then finally, I'm going to start with 3 moles of water. Again, I'm going to calculate the molar mass of water by adding up 2 hydrogens and 1 oxygen. And we get 54.0444 grams of hydrogen. Now, we haven't really proven the law of conservation of mass part yet. To prove that part, we need to add together our reactants, and when we add those together we get 142.0 0.0624 grams of our reactants. And we need to add together our products. And we get 142.0624 grams of our products. So we have proven the law of conservation of mass, okay, as asked in the question. Question number 7 says, explain the statement, mass and atoms are conserved in every chemical reaction, but moles will not necessarily be conserved. The first part of that, mass and atoms are conserved in every chemical reaction. That's because that's the law of conservation of mass, right? So the law of conservation of mass states that mass and atoms are conserved. Remember, conserved means we have equal numbers on the reactant side and products, right? We just proved the law of conservation of mass with that last problem, okay? So that part of it has to be true because that's the law of conservation of mass. But the second part of that now says, but moles will not necessarily be conserved because moles are not, they don't have to have equal numbers. Occasionally you'll have a reaction where your moles are equal, but that's not normally the case, okay? So it's really only mass and atoms that have to be equal on both sides of your equation. Question 8. Interpret the following equation in terms of relative numbers of representative particles, numbers of moles, and masses of reactants and products. So again, we're going to use our coefficients here for representative particles. We have to look at our substances. Potassium is an element, so we're going to have 2 moles of atom. Water is a molecular compound, so we're going to have Sorry, I shouldn't have said moles. Let me start over. Sorry about that. Getting ahead of myself. Okay. Interpreting this in terms of representative particles. The representative particle of an element is an atom, so I have 2 atoms of potassium. The representative particle of a molecular compound like water is a molecule, so I have 2 molecules of water. Potassium hydroxide is an ionic compound, so I have 2 formula units of potassium hydroxide. And hydrogen is a molecular compound, so I have 1 molecule of hydrogen. So that's how I interpret that in terms of representative particles. Again, the coefficients tell me the relative numbers. Okay, so to interpret this in terms of moles, remember, again, our coefficients tell us relative numbers. So we have 2 moles of potassium, 2 moles of water, 2 moles of potassium hydroxide, and 1 mole of hydrogen using those coefficients. The last part of this asked us to interpret this in terms of masses. Remember, that requires math. So again, we have 2 moles of potassium. We're going to use the molar mass of potassium. Okay. To figure out that's 78.196 grams of potassium. We're going to use water's molar mass, which we just calculated in one of the previous problems. Okay. Potassium hydroxide, 2 moles of potassium hydroxide. 1 mole of potassium hydroxide has a molar mass of 56.0 1049 grams. So again, you do that math. And then 1 mole of hydrogen, molar mass of hydrogen. I add up 2 hydrogens.